On the 12th of September 1962, President John F. Kennedy made his famous speech about landing a man on the moon by the end of the decade. At this point in time, NASA had just several hours' worth of human spaceflight experience. Many Americans had accepted that the space race would be won by the Soviet Union, who had already claimed the records for launching the first satellite and the first human into orbit. So in order to achieve their goal of reaching the moon, NASA would need to develop much larger rockets with engines more powerful than anything they had made before. But scaling up to a much larger rocket design sent NASA engineers into a new world of complex problems. In this video, we're going to look at the issues that NASA had with their F-1 engine. We're also going to look at how they fixed these issues and the unusual method they used to test it. In order to lift the enormous Saturn V rocket off the launch pad, it required 5 F-1 engines on the first stage, each capable of producing 1.5 million pounds of thrust. In order to achieve this amount of thrust, massive amounts of RP-1 fuel and liquid oxygen had to be pumped into the thrust chamber. Here the two propellants would combust and lift the Saturn V away from the launch pad. The first stage alone would burn through an entire Olympic swimming pool's worth of fuel in just over 2 minutes. The company tasked with making such a powerful engine was Rocketdyne. They had designed the F-1 engine several years before for the U.S. Air Force, but after the Air Force couldn't find a use for such a powerful engine, development was stopped until NASA came along. In June 1962, Rocketdyne were ready to perform a long-duration test of the F-1 engine. But as the engine ignited and the turbopumps spooled up, the test came to a catastrophic end when the engine exploded. It took several more explosive tests before the engineers finally found what was going wrong: combustion instability. This is where the propellants in the thrust chamber burn unevenly and cause enormous pressure swings inside the chamber. As one area of the chamber fills with more oxygen, it produces more heat, which pushes the flame around in the thrust chamber. The reason this was so catastrophic in the F-1 engine is because these pressure swings were happening 2,000 times a second, enough to completely rip apart the engine. At this point, the Apollo program was well underway, and NASA needed a fully capable engine for the first crewed flights, which were just a few years away. But since an engine of this scale had never been made before, the solution to this problem wasn't going to be obvious. Engineers started to focus on the injector plate, which feeds the fuel and oxidizer into the thrust chamber. The original design was a single large plate with multiple injection holes. Although this was a common design, previous engines never suffered from instability since their thrust chambers were much smaller and the propellants were more contained. In order to solve this critical issue, Rocketdyne engineers looked back to one of the very first rocket designs, the V-2 rocket. This rocket was developed by the Germans during the Second World War, but it contained the perfect solution to fix the F-1 engine. Instead of a single flat injector plate, the V-2 featured several different nozzles which separated the combustion into different streams. The engineers believed that the more controlled sections in the V-2 engine eliminated the possibility of combustion instability. In order to translate this theory onto the enormous F-1 engine without a complete redesign, engineers added a series of baffles to the injector plate to split the combustion up into different zones. After experimenting with many variations of baffle designs, the engineers came across a layout which seemed to stabilize the combustion. The new design was put to the test, and sure enough, the engine executed a flawless burn. But the engineers weren't convinced that the problem was fully fixed. Many worried that once the engine was in flight, the extra forces and vibrations could reintroduce instability back into the engine. So, in order to fully test the new design, NASA placed a small bomb in the center of the injector plate and set it off as soon as the engine fired up. The idea was that a small explosion within the engine could create an enormous amount of instability, far greater than the engine would naturally receive. When the bomb went off, the flame inside the engine became completely unstable. But almost instantly, the baffles on the injector plate started to dampen the pressure swings, and the combustion became stable again. NASA performed multiple explosive tests in order to make sure that the combustion instability had gone. From the first Saturn V launch to the last, 65 F-1 engines propelled multiple astronauts into space without any instability problems. Looking back to a time when rocket engines were designed using slide rules, the ingenuity that was required to overcome these monumental challenges is spectacular. And although we have yet to return to the moon, we can appreciate the incredible genius and dedication that went into achieving Kennedy's goal. Thank you very much for watching, and I'll see you in the next video.